Hello, this is a physics video from Young and Freedman's University Physics. This is the fourth video I've done on a section called electric field calculations. The first video basically covered the theory in this section, which is not very involved actually. Was even able to put in a little example on a dipole in that one. And in the three videos since, I've been doing the examples that Young and Freedman have you do. The way he's done these examples are nice because he hasn't used actual numbers. He's just used the variables. And so what you end up with after each example is a formula that you can use later, as we're going to do here. But let's stop talking and get into the actual details here. So this example is a uniformly charged disk. We used to have, in the good old days, we had CDs, you know, we put them into our computers, we put them into our CD player, we listened to music. So a charged disk, it's a two-dimensional disk of evenly distributed charge. A disk of radius R, there's R, with a uniform positive charge, so there's the same charge everywhere, with positive charge density. Positive implies that the fields are coming out, rather than negative where the field lines would be drawn going in, of a evenly uniform positive charge density sigma. And by charge density, we mean charge per area. We could do it for the whole thing, right? The whole thing, charge Q, divided by the whole thing, A, area, Q over A. But what we're interested for this problem is the infinitesimal charge per infinitesimal area, which will be the same thing. So sigma, the charge density for two-dimensional things, is dq, not Dairy Queen, per dA. Okay, right? And we want to find the electric field at point P, which is nothing there. It's like we're imagining things. You know, we just want to say, how do I find the electric field at this point? At distance x, so x is a constant, not a variable, from the center of the disk. All right. So we've already said that the charge density we can express as infinitesimal q per infinitesimal a, dq dA, per dA. And dA, the infinitesimal area, we're going to think of this disk as being made of an infinite number of infinitesimal rings, which means that we can pull in from a previous example, this I fell into a ring of charge. Anyway, in a previous example, again, he didn't use actual numbers, so our answer is a formula. The formula for the point charge, electric field charge from an individual ring. It's a very similar problem. And so we're going to use this formula we came up with in a previous example. And so one of these little rings, what is the infinitesimal change in area of one of these little rings? Well, it's going to be dr, the infinitesimal width, times the circumference of this ring, which is 2 pi r. Okay, whatever the radius at that point is. So this is not big R, the total radius. This is the R from the center to wherever the ring is. Okay, so let's do it. This disk. What is the point charge from a disk of uniformly charged disk? Okay. So we've got that, we've got the formula there, let's dig into it. So we've already said some of this. Charge density sigma is equal to infinitesimal change in charge per infinitesimal area, okay? Infinitesimal charge per infinitesimal area. And the infinitesimal area is the circumference of any particular ring times the dr of the total radius, okay? That is the little infinitesimal increment of the total radius. Okay, so if we multiply both sides by dA, we end up with dq equals s times dA, and this is dA, so here we have it. dq, infinitesimal charge, is the charge density times 2 pi r, the circumference of a ring, times d big R, okay? D big R. All right, okay, should have probably put big R there. So, and then we're going to import this formula that we got from a couple examples ago. Put it all together, and you turn yourself about. So, if we take the differential of both sides, then we have the infinitesimal x component of the electric field equals all this stuff plus the infinitesimal charge. Okay, great. Now let's take this for dq and plug it in for dq, and we're left with a lot of junk here. Okay, but do you see where we've gotten that? We took the formula from the ring of charge example, and then we've substituted this in for dq in this situation. Okay, now we can say that the y components all cancel out. That's been the great thing of the examples we've done in this section, is they've set it up, x being from the center of whatever, so that all of the y components cancel out. Great. So all we need to worry about is the x component of the field. So we're going to integrate all of those. We're going to add up, ring, 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 ring. We're going to add up all of those infinitesimal rings to find the field point at that out there. So it's going to be the integral from 0 to big R of the total radius of the disk times all of this stuff that we just came up with on the previous slide. Okay, so the next thing we're going to do is we're going to pull out all the stuff that's constant. So sigma, the charge density, is a constant. Pull it out. X is a constant because it's the distance. It's not a variable. It's the distance from the disk, which we're not varying that. We're just asking at this point, fixed point. So the X comes out. 2/4 is 1/2. So the little cancellation there. Pi divided by pi is 1. So the pi, no more pi. Epsilon naught pulls out a constant. So we pull all the constants out, and then we're left with this. Again, remember, X is not a variable. R is the variable here. All right, so let's use the substitution method to take this integral. So we're going to let all this equal u. And so what's the derivative? What's du going to be? Well, X is a constant. It goes blop, and then 2r is going to be basically what du is. And I've got an r up here. I already have an r, rdr, yay, r. So everything's good. So I can say u to the 3/2, and I'm going to take a 1/2 to get rid of the 2r. Then the 2 and the 2's cancel out. And I can say that this, and by the way, I'm leaving the constant part away so that I don't have to type as much. So this integral here equals this integral here, which is going to be negative u to the negative 1/2. How did that happen? Well, remember, when we take the integral of something, given the fundamental theorem of calculus, we end up with something that if we take the derivative of it, we get this. So what happens when I get the derivative of this? Well, 1/2, you subtract 1 from the exponent, it becomes negative 3/2, which is, this is negative 3/2, yay. And also you multiply the front, so the negatives will cancel out, which will make it positive, yay. And then 1/2 will end up with 1/2. All right, so this is indeed the integral of this, because when we take the derivative of this, it gets back to this. And we're gonna do this from r to 0, okay? So when you plug in, well, first of all, I left out some steps here, I'm sorry. So u is this, so we can let it come back. The u comes back. And so this to the negative 1/2 is 1 over square root, that's 1/2. Negative 1/2 means it's in the denominator. And when we plug the r in for r, we get x squared plus r squared, okay? And it's negative, so that's the r. And then the 0, when r is 0, we're just left with 1 over the square root of x squared. Well, square root of x squared is x, so that's where that comes from. Okay, right. So that's the answer. So there we have it. So if you want to know what the electric field is at a point away from a charged disk, the y's are going to cancel, and we're left with E x dimension is this. All right, now we're done with this section, and we can move on to the next one, which I think is on electric field lines.